So our next talk is going to be a little bit of a shift from some of the fish biology that we've heard, but we're excited to also share some work that's been completed on groundwater recharge. So our next presenter is Dr. Helen Dahlke. Dr. Dahlke is an associate professor in integrated hydrologic studies in the Department of Land, Air, and Water Resources at the University of California, Davis. She obtained a PhD degree in environmental engineering from Cornell University. Helen's current research interests include surface water-groundwater interaction, water resources management, red host zone transport processes, and applications of DNA nanotechnology in hydrology, which is super interesting. One of her main research efforts focuses on testing the feasibility of using agricultural fields as recharge sites for groundwater banking. And with that, I'll hand it over to Helen. Thank you.
Thank you very much. Can you confirm that you see my screen?
I can see your screen and I can hear you fine.
Okay, great. Excellent. Thank you very much. And thanks for sticking around. Yeah, so as mentioned, this is a little bit a shift in topic here. We were tasked actually about 5 years ago, approached by the Bureau of Reclamation to look into managed aquifer recharge as a means to potentially provide more flow to rivers in the Central Valley. And so with this presentation, I would like to show some of the results and some of the work we've done. And I would like to thank a lot of my students and postdocs and collaborators who have worked with me on this study. You might have seen similar slides like this one from the Department of Water Resources. California is a land of extremes. We have drought years and then we have extreme flood years where we actually don't know what to do with the water. And so sometimes we have so much water that it's really causing quite a bit of flood damage. And so when the Sustainable Groundwater Management Act came around, which was passed in 2014, and shortly after, the Department of Water Resources also initiated the so-called Floodmore program, which is interested in using working landscapes as flood areas or flood zones to recharge potential excess water into the ground. My lab is mainly working on the idea of diverting these high flow events, or at least a portion of stream flow during high flow events. So when we have big precipitation events occurring, an increase in flow, flood flows. And this was actually recently made possible, even more so, by the State Water Resources Control Board, who allowed now the diversion of so-called high flow events for groundwater recharge through a streamlined permitting process, which you can see or access here at this URL link. And they actually adopted one of our recommendations, and that is defining high flow events by using the 90th percentile of the flow record. And the State Water Board is now allowing the diversion of high flow events between December and end of March for groundwater recharge. The research we're mainly working on is actually using agricultural fields or cropland for winter recharge. So instead of going with the classic infiltration basins, we're basically looking into an alternative when we have a wet year, such as in 2017, where we had a lot of rain. Many classic infiltration basins were running at full capacity and couldn't take more water. And then it's really a question, where can we find areas that can take additional water? And one of these logical go-to areas might be agricultural fields that are already connected to surface water conveyance infrastructure that would allow us to divert water from rivers onto fields and have it infiltrate. But there are, of course, many factors that go into adopting such a practice, and a lot of farmers who are thinking about adopting this practice have concerns. So most of our recharge is looking into addressing some of these concerns, such as water quality, leaching of nitrates, or crop suitability if you have a perennial cropping system planted on the fields. But I wanted to start with the debate about suitable recharge locations. And so for this research project that we have with the Bureau of Reclamation, we focused our research efforts on the Tulare Irrigation District, which is located in the southern Central Valley in Tulare County. Yeah, it actually includes the city of Tulare, which is kind of here in this area in case you see my mouse. And here we approached farmers to do on-farm experiments, and we also started with a site suitability analysis. And one of the layers we took for this analysis was the so-called Sagby index, Soil Agricultural Groundwater Banking Index, which is a soil-based index that allows sort of a quick assessment of which soils can take a lot of water, have a high infiltration rate versus, you know, which ones are clay, rich or fine textured soils that might not be so suitable for taking additional water. And so within this district, we identified about 43,000 acres that had some sort of connection to the existing surface water conveyance system. And of those 43,000, about 25,000 acres actually had soils that are rated as moderately good, good, or excellent. So meaning they look very promising for potential winter recharge activities. For those of you who are not familiar with Sagby, this is a tool developed by one of my colleagues here at UC Davis, Toby Eugene. It's available as an online tool. You can look at it. Yeah, you just have to Google Sagby, you will find it. And it's quite interesting because it ranks and rates different soil properties and such as root zone residence time, or it considers if there's chemical limitations such as high acidicity in the root zone. But it's actually a fairly nice and quick way of assessing whether or not your field or your farm is suitable for potentially taking on water in the winter for recharge. So here's actually one of the more detailed maps we created. The blue lines show the surface water irrigation or surface water conveyance systems in Tulare Irrigation District. And then you can see clearly those field boundaries of individual parcels. And we focused our effort on alfalfa and pasture fields and fields that were planted with nut trees, and then approached farmers to see if they had some interest in working with us. And we did identify 2 fields on which we did some winter recharge experiments. And some of these fields, we applied quite a bit of water. So one of those fields, the southern one here, was a pistachio orchard, shown here on the left. And the other field was a 22-acre field planted with alfalfa. Both had fairly good soil ratings and should look promising for recharge. And so in 2017, which was the wet year, we applied about 147 acre feet on the pistachio orchard, and only 9 acre feet on the alfalfa field. We were hoping to get more, but unfortunately it didn't happen. The field was not as well connected to the excess water that was available. But in both cases, we were looking also into yield data, as well as how the winter recharge is potentially leaching some nitrate that might have been left over in the root zone from previous growing season activities. And it's actually quite interesting. So 2017 was more or less a really wet year right after the 4-year drought we experienced between 2012 and 16. And so we took cores before we flooded the fields in the winter, which was over 20 days in March. And then we took soil cores to about 3-4 meters depth after the winter flooding, and looked how much nitrate, residual nitrate present in the soil had been leached. And you can see here the numbers. We had actually in this pistachio orchard, we had a very high residual nitrate load in the root zone or shallow vadose zone. So almost in one core, we had almost 3,500 pounds you can see here, and most of this has actually been leached during the recharge event, which can cause quite some adverse effects to groundwater quality. And so one of the recommendations would be going forward to have some soil testing done, for example, before we do flooding, and to estimate how much water is actually needed to make sure that the nitrate load is diluted enough so it's not causing an increase in nitrate loading in the groundwater. Here are some of the profiles of the soil cores we took. First of all, it's really astounding when you take these cores on these fields, how heterogeneous the soils and the vadose zone are. There is not one core that looks exactly the same as the other one. So here on the left, you can see, for example, a core that has a lot more finer materials, so silt loams, sandy loams, loamy materials, and on the right one, you can see one that's mainly just sand. And those sands are the ones that are leaching really well, so where you have more or less no retention of nitrate in the profile. While for the more loamy core, the applied water is just more or less moving the load a little bit further down in the profile, but it's not really completely removing it. So because we're really interested in how this winter recharge activity is influencing potentially the nitrogen cycle, and particularly how much it's leaching some of the nitrate to groundwater, one of my PhD students, Nick Murphy, has started to develop a hydrous model, which is a physically based model capable of modeling saturated, unsaturated flow, solute transport, and any biogeochemical reaction you can think of. And so we coupled hydrous with this code from USGS, which is called Freaksy, which has all kinds of aqueous geochemical reactions already programmed to simulate some of the basic processes in the nitrogen cycle, and to see how various soil textures are influencing the nitrogen cycle and nitrate leaching. And so I wanted to show you some of these results from the model. And the model needs, this is just a graph here of the nitrogen cycle. You might remember that from undergraduate education. But the model needs more or less, or is predicting or simulating just like 4 or 5 parameters in the nitrogen cycle. So the organic nitrogen content, ammonium nitrate, it needs organic carbon content information, and then it can also create an estimate of atmospheric nitrogen leaving the system as an output. And the main processes that we're modeling with the model right now are mineralization of organic nitrogen to inorganic nitrogen, which then of course can become available for leaching. This often happens if you increase the moisture content in the root zone, but you keep oxic conditions. We also simulate nitrification of ammonium to nitrate, denitrification, which would then result in some gaseous losses to nitrous oxide. Often that happens under anoxic conditions. And then, of course, most importantly, we're interested in knowing how much leaching is occurring of nitrate to deeper layers. And so here are some of the results from the model. This is again from the pistachio orchard. Some of the soil moisture data we collected. We did apply water in early March of 2017 in several sort of pulses. And yeah, so and then you first start by calibrating the model on the hydrological side, and then we do some calibration of the biogeochemical performance of the model. And some of these nitrate profiles before and after the flooding are shown here in the top, in the bottom right, and the blue dashed line is the simulated profile. And on the left, you can see here the nitrate mass balance before and after the recharge or the flooding for recharge. So based on our estimates, the amount of water that we applied, 147 acre-feet on this field over 20 acres, was really not enough to leach nitrate below 3 meters depth. So it definitely did not reach the groundwater table. But the amount of nitrate we leached was about 218 pounds per acre, which translates to a bulk concentration of about 10.9 milligram per liter, which is just slightly above the minimum contaminant level of nitrate that we have for groundwater in California. However, I wanted to point out using a reactive transport model definitely has its advantages, because in comparison to a conservative 1D model, which just assumes nitrate behaves conservatively, does not change into, for example, nitrous oxide through denitrification, we would actually have leached about 4,600 pounds per acre, so a much higher amount, which is probably not true. So the reactive transport model does capture ongoing processes in the root zone much better. In the sandy core that I just showed you in the previous slide, we leached about 184 pounds per acre. Somehow the window with me popped up. Can you see still my slides?
Yeah, we can still see your slides.
Okay, good. I just saw my window with me speaking popping up. So yeah, so overall similar amounts of nitrate were leached in the sand and the loamy profiles that we took in the field. We also looked into high flow water availability. There is a stark contrast, of course, between the northern part of the Central Valley and the southern part. And in general, there is less high flow available, and most actually rivers are fully allocated in the southern Central Valley. But if you look at some of the observed flow data, you do actually see some availability here and there along some of the rivers. And for the Kavia River, which is the one feeding into Tulare Irrigation District, this is sort of the record we see for the flow available above the 90th percentile, so the 10% largest flows. And in some years, we've seen about 500,000 acre-feet of water. But in recent years, definitely less and less available. We've used this flow data and use it in the C2VSIM model, which is an integrated surface water groundwater model developed by the Department of Water Resources to estimate how recharge would influence groundwater storage, groundwater tables, and return flows to streams. And we ran here for this model 3 different scenarios, again, focusing on areas that have good soil suitability for recharge using the Sagby index. So we looked into 3 scenarios on recharge on excellent soils, excellent and good soils, and excellent, good, and moderately good soils, which are all indicated here with different colors. And we diverted stream flow above the 90th percentile for groundwater recharge. And here are some of the results from this modeling exercise. On the right side, you can see a cumulative graph of how groundwater storage has changed over the years if we were to start recharging, on a regular basis. Here in this model exercise, we started in the 1930s and of the historic period. So, and then, after maybe 80 years, you would see an increase of about 500 million cubic meter in groundwater storage for the best scenario, which is recharge on excellent and good soils. And on the left, you can see how the groundwater table is responding. And you can see clearly that where you're recharging has a big influence on how the groundwater table is responding, because often recharge causes a groundwater mound to form. And the top 3 panels here show the results for the most shallow unconfined aquifer, and then the green panels show it for the semi-confined aquifer, which is often a little bit deeper. So on average, we do see an increase of about 1 meter or more in some of these areas where we did recharge. And just to show you a little bit the water balance here, I'll walk you through this. So in our modeling, we diverted about 1,500 million cubic meter of water for recharge, which translates to about 1.2 million acre feet. Some of it increased storage, about 1/3 went to an increase in groundwater storage. But the majority actually went back into streams as return flow to streams, so contributing more base flow in our rivers in that area. And that's probably what is the most beneficial outcome, long-term outcome of groundwater recharge, if you're concerned about minimum flows and also stream flow temperature in rivers carrying salmon. Before I will come to an end here, I wanted to point out another little tool that we've developed, which is available here at agra.ucdavis.edu. This tool here shows you suitable land parcels, agricultural land parcels, that could, if you were to do recharge on these land parcels, it would have a clear benefit on the water supply, groundwater dependent water supply in rural communities, impoverished communities, of which we have many in the Central Valley. So if you are thinking about groundwater recharge activities, I encourage you to consider some of these location suggestions to create multiple benefits for the recharge. So not just groundwater storage gain, but we can also actually help shallow domestic wells that have run dry, for example, during the drought, by recharging near those communities and have those waters, those recharge waters flow towards those domestic wells. This is a study that was done by my master's student, Nisha Moraha, using a variety of geospatial data sets. Again, the Sagby index is in here, land use, but we also looked into some socioeconomic data to estimate how vulnerable some of these rural communities are to groundwater change, groundwater supply change. And we also used a groundwater flow model and particle tracking to estimate capture areas of domestic wells in rural communities to see where recharge could benefit those communities. And so here's just like one of the maps that a close-up of these suggested recharge locations for the Tulare Irrigation District. In orange and green, you can see those rural impoverished communities, and the blue parcels show suitable sites for recharge that could benefit the wells in those communities, given that they are within a certain flow direction of the groundwater. And the left map shows the locations of all disadvantaged communities in the Tulare Lake Basin. So with that, I would like to summarize. On-farm recharge is really a viable option in regions where large amounts of excess water is less frequently available. So we mainly see it as a supplement to ongoing, traditional infiltration basin operations. For years, when you have really an huge amount of water available and you don't know what to do with it, then just put it on fields and recharge it to the ground. We've shown through modeling that it can increase groundwater storage and return flows to streams. And if you place those recharge operations near rural communities vulnerable to, for example, well failure, it can have additional benefits for those communities. However, we also recommend final site selection should be carefully done based also on the ground surveys, since our soil agricultural groundwater banking index, for example, is not a guarantee that it's really a absolutely suitable site. So we definitely recommend field level studies before implementation. And with that, I would like to thank everyone for listening and my collaborators, and I'm open for questions.
Yeah, Thank you, Dr. Dahlke. We actually have a few questions for you, but we are running a little bit over, so we've posted them in text. It looks like Will Halligan is looking for some information on citations and references. If you could provide that in text on the slide for him. And Matt Myers had a question for you about, that you answered a little bit about how recharging groundwater was contributing to base flow in rivers. But if you could just take a moment and just answer those on the side. We're going to do a quick 5-minute break for everybody, and we'll come back at 11:35 to continue with the final section. So thank you so much for your talk. We appreciate it.
Thank you. Yep.